Wow, we're almost to the end of the semester. Chapter 11. There's two main ideas in this section. One is basically like these two problems. Some type of distribution has been claimed. So over here, I claim that the grade distribution is even. In other words, there's the same amount of A's, same amount of B's, same amount of C's, same amount of D's, and same amount of F's. Which, hopefully you can see that's just not true. Then it could be one like this where percentages are given. I claim that out of these people from Hartnell College, 70% are going to be Latino, 15% are Caucasian, 5% are Asian. Now, notice that this adds up to 90%. So that's just fine. It can be a claim that says, I think that's what it is for Latino, that's what it is for Caucasian, that's what it is for Asian. It's not saying 100% of the people, it's just saying, I'm making a claim about these three groups. So these are the two types of goodness of fit tests, they're called. And then we're going to have 2x2 contingency table after that on page 2. So the first thing we need to do is, for this, we need to find the total sample size. N equals what? So let me see, this would be 31, 39, 42. N equals 42 people total. Then, if you have 42 people and they're going to be divided evenly amongst 1, 2, 3, 4, 5 categories, then you would just have 42 divided by 5 categories. That means that on average there would be 8.4 people in each category. So for this one I'll put 42 divided by 5, but that equals 8.4. So in theory, there should be 8.4 people in each category. And it's actually only the C's that are even close to that. So next, the test statistic is going to be chi-squared, which goes like this. Add up the following. Take each observed value, subtract the expected value, square that, and divide by the expected value. So it's basically saying how much is it off by? And divide that by what you expected it to be. So it's basically, in a way, trying to find out, well, what percent is it off? Although the squaring gets rid of negatives. So it's almost like percent, but not quite. Okay, so then it's going to be chi-squared equals, so 14 minus 8.4 squared and divided by 8.4. And then 17 minus 8.4 squared and divided by 8.4. Next, 8 minus 8.4 squared and divided by 8.4. And then 1 minus 8.4 squared and divided by 8.4. And lastly, 2 minus 8.4 is squared and divided by 8.4. Good time for the calculator. So since they're all divided by 8.4, what I'm going to do is just add the numerators and then divide the whole thing by 8.4 at the end. Save me some typing. And then the next one is 8 minus 8.4 squared. And then I've got 1 minus 8.4, that's squared. And last 2 minus 8.4 parentheses is squared. And then that whole thing, all of them were divided by 8.4, so that's the common denominator. The grand total is chi-squared equals 23.952. And then we need the distribution, so chi-squared looks like this. 0, it starts at, because they are all squared, so it can't have negatives. This is a right-tailed only test, so with alpha equal to 0.05, that means that this is the right tail. And then what about degrees of freedom? Well, degrees of freedom comes from the number of categories minus 1. 5 minus 1 is 4. So then on to the chi-squared table. Boy, I really need a new chi-squared table. Maybe for my birthday. So it's a right tail, and we've got 0.05. Degrees of freedom is just 4, so we're just right here at 9.488. So the critical value, 9.488. So does a 23.9 go past that? Yes, it definitely does. And so we definitely can reject that claim. So reject the claim of an even distribution. So it's not true that in that class grades were evenly distributed. As you can see, there were a lot more A's and B's than there were D's and F's. Thank goodness. Okay, then on to this one. So now we have to do the percent. Oh, first thing we have to do is add this up. So this would be 50, right? 38 plus 9 plus 3. So n equals 50. So first of all, n is equal to 50. So this one should be 70% of 50. So that would be 35 people. This one should be 15% of 50. 15% of 50 is 7.5 people. And this one should be 5% of 50. 5 times 5 is 25, so that would be 2.5. So actually the numbers aren't off by too much. This is only off by 3, only off by 1.5, only off by 1/2. So then we've got our chi-squared is going to be 38 minus 35, square it and divide by 35. Next, 9 minus 7.5, square it and divide by 7.5. And then 3 minus 2.5, square it and divide by 2.5. So on the last one, they all had denominators of 8.4, so I was able to do that at the end. Here, the denominators are different, so I'm going to have to type in each fraction. So 38 minus 35 is squared and divided by 35, plus 9 minus 7.5 is squared and divided by 7.5, and there's 3 minus 2.5 squared and divided by 2.5. This one looks like it's going to be a fail to reject. Okay, so again, the distribution is chi-squared. It starts at 0. This is a right tail only test, so alpha equals 0.05 in the right tail. Critical value comes from table A4. And we have degrees of freedom is the number of categories minus 1. So degrees of freedom is 2. So degrees of freedom 2 and 0.05 means it's this one, 5.991. And then the question is, does a 0.6 go past a 5.991? The answer is no. So that means fail to reject. We cannot reject the claim. So basically those are the two possibilities for what's called goodness of fit test. So in other words, how well did this data fit with what was expected? In this one, we cannot reject those percentages. The other one, we were able to reject that they were equal. All right, then on to the last part, which is actually a more interesting, more useful idea, and that is a 2 by 2 contingency table. So basically we've got the idea that someone could be male or female here, and then these are grades from a trig class. So you could have, a person could have been a male or a female in the class. Also, there's the information about what score they got in the class. So we basically have score and gender as two main variables. And what we're trying to do with the contingency table is see, is there a relationship between someone's gender and their score? Or, in other words, who did better, the men or the women? So we could say over here is going to be the idea of gender. So these can be male, these can be female. And then over here, what I need to do is split up their scores. These were scores on a particular exam. I think it was exam 3. Anyway, so now I have to decide how to divide that. So you could look through the scores and try to guess what the average is and have that as a dividing point. Or you could pick something that you say, well, passing the class and not passing the class, that's sort of an important thing. So that would be a cutoff of 70. I do want to be able to cut it so that like half of the people are going to be here and about half of the people are going to be here. And looking at it, there's actually a lot of people that are above 70. So I'm going to make it 75. I'm going to make the cutoff 75. So those people that have less than 75 and those people that have bigger than or equal to 75. Okay, so for the men, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. There's n equals 22 men. So when I'm done, these two boxes should add up to the 22 men. So now I'm going to highlight the men that have less than 75. By highlight, I mean just going to put a dot by them. So if they have got less than 75, so strictly less than 75, this one doesn't count. This one's going to count over in this group. Wow, come on guys. Bringing us down. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 men that got less than 75. That means there should be 8 that are not highlighted. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8. Sure enough, 8. All right, now do the same thing with female, less than 75. 1, 2, 3, 4, 5, 6. That's a good reason for double checking. 1, 2, 3, 4, 5, 6. So there's 6 here, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so this is a situation where we're probably going to get reject because this has the bigger number on top and then the smaller number. This has the small number on top and then the bigger number, and it's because the women did better on that test. Okay, so the claim is that the score and the gender are independent. So person's score and their gender have nothing to do with each other. That's what the claim is with these 2 by 2 contingency tables. It's always that they're independent. And then it's going to be chi squared It's going to be a right tail only test. And we can do this one with the calculator. So the first thing we need to do is enter this little matrix right here. So if you haven't done matrices before, they're right here. So it helps if the calculator is on. Then you go second matrix, and then just choose A. If it doesn't say these numbers right here, don't worry about it. Oh, sorry. I forgot one step. So you go second matrix, and then move over to edit. And if it doesn't say these numbers right here, don't worry about it. Just hit enter. So our matrix is 2 by 2. It always goes rows first, 2 rows and 2 columns. So 2 rows, 2 columns. And if you've never used this before, then it would just put zeros in here as a placeholder. Then you can just type over the numbers 14, 6, 8, and 12. Once you have the matrix loaded and ready to go, now I go back to stat and good old stat tests. So it's going to be towards the bottom. Oops, under tests. And it's right here, the chi-squared test. So once you do that, it's going to ask for you to put the observed values in matrix A. This is telling you that it's going to put the expected values in matrix B, which we will get to in a little bit. And then we need the test statistic. So the test statistic is a, oh cool, it's a 3636. So test statistic chi-squared equals 36.36, no, 3.636. Oh, it's not even on the screen, sorry. So there's the test statistic. And the calculator tells you degrees of freedom was 1. Degrees of freedom comes from take the number of rows, subtract 1. Take the number of columns, subtract 1. Whatever you get, multiply those two numbers. And that, for us, would be a 1 times 1 equals 1. So it's going to be degrees of freedom equals 1. Chi-squared is table A4. It would be 0.05 for the right tail, and if it's degrees of freedom of 1, then it's 3.841. So the critical value is 3.841. And then, does a 3.6 go past a 3.8? The answer is no. It was close, but no. So probably if we would have had just a few more students here, then we would have had enough evidence, but not here. So fail to reject H sub O. We cannot prove anything here. All right, one last thing is the expected values. So like I said, those are in matrix B. So if you go to second matrix, and on this screen right here under names, then choose number 2 or B, and then hit enter to see what the matrix actually looks like. And then these are the expected values. So in other words, if your gender has nothing to do with your grade, then here's how it should have been split up. It should have spun up 11 people here, 9 people here, 11 people here, and 9 people here. And you can see that these are off by a bit, but they're actually all off by 3, aren't they? But that still wasn't a big enough sample size to actually prove it. One last note is that these things are all supposed to be bigger than 5. If they're not bigger than 5, then most likely when I chose this 75, I chose it wrong. But all of these are bigger than 5, so the test results are valid. And there's contingency tables.